Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Charlie Zhu of Cyber Optics. We're going to talk today about deep learning in industrial inspection. Charlie, we've heard a lot about AI coming into all sorts of parts of the manufacturing, but deep learning is really going for much more data, much more analysis, and basically a lot more accuracy, right?
That's right. Edward, first, let me thank you for giving us this opportunity to share our experience and our learning curve with adopting the deep learning. Yeah, so along the way, we have been trying different methodology to try to solve the complicated problem, which is difficult to be solved by the traditional image processing algorithm. And so recently, with the advancement of deep learning, we are seeing a more and more adoption and success with the deep learning. Yeah, as you mentioned, it's not just only the accuracy, but also the complexity of the problem itself. So deep learning really fits into that domain, and using its deep and complicated network architecture, it can mimic the way that humans' brain is working, which enables it to solve these kind of problems.
Let's take a closer look.
Sure.
Charlie, what are we looking at?
This is corner field underfield for IC packaging. This is a common process nowadays for memory like SDRAM and SSD products.
And so why do you need deep learning in this? Is this more than the human brain can actually see and comprehend?
Yeah, that's a very interesting question. Let me explain the underfield or corner field a bit. It's basically the material bonding the IC to the substrate. The problem is that sometimes there's a defects during the dispensing process, and the customer want to inspect the corner fields after the IC is placed. The difficulty is because the underfield, as its name implies, is under the IC. It's hard to be seen by the normal cameras. So here we are using side cameras, but even the side cameras, we can't see the complete picture of the corner field. That's why it's a challenge to use a vision algorithm to do the inspection.
So what does this actually look like in terms of you finding a defect or some sort of problem?
Yeah, so this is kind of an example of the problems we are facing for the corner field. You can see from the side images, you kind of see some white stuff highlighted by the red here. So this is actually the corner field. The problem is when we are using the traditional algorithm, it's just catching the blobs at a different segment. It doesn't see a continuous blob of the corner fields. While the inspection criteria actually measure the length of the whole corner fields. So with these segmented corner field blobs, we are not able to measure its actual length. But what you can see here is by the human's naked eye, when you do the visual inspection, you can kind of see where the corner field is from the bottom right corner all the way to the middle. So this is a good continuous corner field. But by the traditional algorithm, it looks like a defective one.
This is the same problem that companies have been wrestling with when they're starting to deal with automotive computer vision, right? Because they're trying to identify objects and figure out, okay, what exactly are we looking at?
Yeah, absolutely. So we are solving similar problems as those autonomous driving. So a little bit background. So in general, deep learning or machine learning are trying to solve three types of problems. The one on the left we call classification. So this is the simplest problem among the three. So basically, you're trying to classify the object in the picture. In this example, is the animal. And the one in the middle is you have multiple objects in the pictures, and you're trying to draw a bounding box around the object and tells which types of object it belongs to. And on the rightmost, we call segmentation. This is in general, it's the most complicated problem to solve. So basically, the algorithm is looking at each pixel in the picture and tells and which object this pixel belongs to and what types of object it is. So for the corner view, or in general, those on autonomous driving, we simplify the problem as object detection. That's based on the requirement of the customers. So the customer don't want to, for example, measure the exact area of the corner view. They just want to know the length and the width of the corner view. In that sense, a bounding box around the corner view is good enough for them. The same for the autonomous driving. So you just want to know the bounding box of like a pedestrian of another vehicle, so you can avoid any collision with them.
These are fairly complex algorithms that you're developing here. Is the inferencing actually built into the inspection machine?
Yes, we build the inferencing into the inspection machine. Let me show you a bit of the network architecture using. So in general, we're using convolution network. So in general, that's kind of a common deep learning network architecture or model. What we are doing here is we customize this network for the problem we are trying to solve. So it's object detection, and also it's customized for the corner view detection. What we customize basically and how many layers and what types of model we use or algorithm we use in each layer. And there's other things whether we are using a normal convolution net or we're using some residue nets so that we can train even deeper network architecture. So these are all the consideration when we design the network. And also we apply some transfer learning so that it can speed up the training process, shorten the time to train the model.
So given what you were looking at for the corner field, what did you actually find?
You find that the network, in the end, the deep learning works very well for these particular problems. So these examples are from the initial feasibility studies. So these are the inferencing results. You can see that it works very well, almost like human eyes. You can see that it finds the corner view and the bounding box very well, even though there's other objects. Like you can see, there's some ICs here. These, I think, is small resistors. And here you even have a big chip here blocking the corner view, which causes all the challenges to the traditional image processing algorithms. But the deep learning on the algorithm we develop here works very well and can find all the corner views in these challenging conditions.
Really what you're trying to get to here is confidence that you actually have done full inspection, that you don't have any latent defects, because you're really looking at everything in great detail, right?
Exactly. So the first thing is we need to have a confidence of whether the one we find is a corner view or whether it's a corner view in these pictures. So these are the bounding laws, and the next slide is showing a few more examples. So these are this corner view on the different sides of the ICs. And you can see their shape actually are different. So these are actually except the center one, the one on the left, on the right, they're the good one. The center one is arguable, probably is a defective one because it's too long. It's connected to the one on the other side. So what you can see here is the algorithm actually can catch the corner view regardless its size and the shape accurately, precisely, probably even better than humans.
So what does a defect actually look like, and how do you know that it's really going to cause a problem later on?
Sure, yeah. There's mainly two types of defects. One is too short, or there's no appearance of the corner view. As in these slides, the middle and the one on the right are the two examples of the corner views are too short. And we are trying to mimic the non-presence on the left. It's a block. So it's actually a special example. Sometimes you will have a falling object fall onto the product. So the user want to catch that, and this could be a good example. But in some cases, and it probably just the corner view or the epoxy is not dispensed. We tried in other cases, we can catch that kind of defects accurately too.
One of the problems in inspection has been things like shadows and excessive reflectivity of different surfaces. Does deep learning capture all this?
Yes, the two things will decide its capability of catch that kind of defects. Basically, we call these kind of variations. So what we are doing here, the first thing is for sure is we need to collect the example of different variations. As in the situation you mentioned, when the lighting is not ideal, for example, the corner field is not at the center of the FOV. For example, when it's at the edge, so its lighting may look a bit different when it is at the center. That's kind of one of the common variation. And the other variation will be the product itself. For example, the color or the reflectives of the surface are different. So yeah, we really need to work closely with the customer and collect all the variation. So that's the one thing we try to solve this problem. The second thing we need to do, as mentioned, is the network itself. The network itself need to be sophisticated enough in deep learning. It need to be deeper enough to learn this kind of complicated problem. But at the same time, it's still possible to train because there's usually the two things conflicting with each other. When the network is too shallow, it's not deep enough, it's not able to solve complicated problem. But when it's too deep, it's very difficult to train. There's all kinds of problems, like you need more samples, and it can be overfitting all these problems. So we need to design the network architecture carefully. And we have a bunch of data scientists, machine learning experts working on this to make sure we have the right network architecture for the customer to solve this problem.
And that's one of the big advantages of deep learning versus machine learning, right? Is that you're going that much deeper into the data to be able to say, here's a problem. We are seeing this in multiple different places, or we've rarely seen this before, or maybe we've never seen this before, and we think there's a problem here.
Yes, exactly. That's kind of the beauty of the deep learning. So there's a lot of things we can customize. And actually, the whole research area is very active. So we need to make sure that we are updated with the related algorithms, technologies in the state of arts and apply it to our applications. On the flip side, it's also make the customer difficult to understand what we are doing. For all the new variation, we really need to help them to train the model. Because look at the traditional algorithm, and we have one actually, a simple machine learning algorithm. The customer actually can train the model by themselves. But with the deep learning, because all these expertise needed, we have to train the model for them every time. And the model training process can take a few days or even a week to generate a new model.
How much does this impact the inspection time, and how big an area are you actually inspecting with this?
Not exactly, I would say. The inference time, of course, is affected by the network architecture. So the deeper it is, it usually takes longer to inferencing, but it's not so correlated with the network architecture as the training time. So we are using the GPU, very sophisticated, advanced GPU for the inferencing. Usually the inferencing takes 1 to 2 milliseconds at most. So in general, a difference can be ignored.
What other applications are there for this?
Oh, there's many other applications for deep learning. I have a few more examples. Seen here is actually a cosmetic defect inspection using deep learning for laptops. In this slide, actually, you can see different types of surface defects or cosmetic defects. They're smudged, so basically they're fingerprints. And you have some more serious defects like chips on the surface and see some discoloring. This one actually a segmentation problem. So what we are doing is we try to draw the area of the defects carefully because it depends on the defect type and also the size of defects. we need to decide whether we should reject this product or not. For example, for this kind of chip defects, these are very serious defects. They shouldn't exist on the product at all. So as long as we detect one chip defects, regardless of size, we should reject this product. On the other side, for fingerprints, this kind of defects can be cleared afterwards. So usually the customer have a higher tolerance of this kind of defects. So unless the size of defects is really big, we shouldn't reject this kind of product with the fingerprint defects.
Charlie, when did deep learning actually start showing up in inspection? We've been talking about it for years, but at that point, it was sort of in the research stage. How far along are we now that's now in active use in the field?
We have been trying deep learning probably around 8 years. But I would say for cyber optics, we start to really apply it in real applications about 3 years ago. I can see as an industry player, at least in our industry, like in semicon, we are seeing, the trend and the roadmap about the same with our competitors.
Charlie Zhu, thanks for a great explanation.
You're welcome.